And welcome to our talk on injecting new kind of a malware into deep learning models and how to defend against them. I am Mohamed Nabeel, and it's a collaborative effort with Alex Taro. We are both from Palo Alto Networks. First of all, I would like to thank the organizers for allowing us to send a recorded video, as unfortunately we were not able to be there in person this time. This is the outline of my talk. First, I will briefly touch upon AI supply chain and then go into the evolving AI threat landscape, followed by our attack tactics, and then show two proof of concept attacks, finally show how to defend against such attacks and provide key takeaways. AI supply chain. Building models from scratch is really expensive. In a recent report from Gartner showed that 70% of organizations will use pre-trained models in their workloads going forward. And this creates an economy for hubs. As you probably might have heard about Hugging Face and TensorFlow Hub. This allows you to upload any models there and anyone else can consume from those places. Think about PyPy and NPM for AI. And this democratizes the access to state-of-the-art AI models to everyone. Now I'm going to walk through the key steps involved in this modern AI supply chain involved in the hub economy. So you design the model, and then you train the model, and then you save it into a serialized format, which results, think of like a zip file, compress everything into one big file. And then you upload that file to the hub of your choice, and anyone can download from there, deserialize it, and load it into their computer in order to either directly use it or fine-tune it and use it with additional improvements. So AI supply chain is in fact software supply chain. These models aren't just data, they are parameters, these weights and biases, plus executable functions. So the key question we ask here is, can we trust these models? And what can we do about it to use them safely? Now let's look at the evolving model threat landscape. Attacks on AI models are not new. There have been numerous attacks earlier. And we would like to categorize these two attacks into two broad categories. One is called behavioral attacks, commonly known as adversarial machine learning, and the other one is carrier attacks, which is the focus of this talk. Behavioral attacks try to change the model decision by intentionally manipulating it. On the other hand, carrier attacks use these models as a carrier to hide malware content, usually not affecting the final decisions of the model. Just to be complete, I would like to briefly touch upon these behavioral attacks, those adversarial machine learning attacks. And there are three main types of attacks in the past. The first one is model poisoning attack. As the name suggests, these are attacks where attacker poisons the training data. So when the model is trained with this poisoned data, it can result in poisoned output or poisoned results, or if it is biased data, it will result in biased output. This could be a huge problem for large models which try to scrape all the data in the internet without paying attention to how trustworthy they are. And the second kind of attacks are called model evasion attacks. This is an inference time attack. This is where the attacker tries to manipulate the input data, just like the figure shown in the left bottom. The attacker changes the stop sign with pasting some stickers. And in this case, the model then incorrectly flags them as instead of stop, it says 45 kmph. It's a very fatal mistake. And the third kind of attack, which is gaining traction nowadays because of the popularity of Gen AI, is prompt injection attack, as the name suggests. These are attacks where attackers inject some kind of a prompt into the existing prompt to make the model behave differently or break or jailbreak the model. So the figure on the right bottom shows how an attacker was able to inject a prompt to go beyond the safety filters of GPT-4. So now, how does the game change for attackers within this model economy? So they will create the model just like before, but here they will try to inject the malicious code into the model before they train it. So after they train it and serialize it, they make sure that this malicious code gets serialized and get into the file. And then once they are in the file and uploaded to the hub, when the users download, they are not downloading clean models. These are models with some kind of a infection. And once they either load these models or do some inference, these malicious codes get activated and it infects their computers. Now, the second kind of attacks, which is the focus of this work, carrier attacks. There are three main types of attacks which we have seen in the past. They are the pickle bomb, abusing custom layers, and hiding invades. Now, I'm going to present briefly about these attacks so that we can go into the new type of attack and show what's new. So the first one, the pickle bomb. Once pickle used to be a common file format to save these models, and the key vulnerability they have is these are not data formats, they are executable codes, and they have this abusable function called reduce, which allows you to call any arbitrary system calls. And attackers use this to ingest malware into the model through this function. And this gets triggered when the model is loaded and through the pickle.load function. Right. The second group of attacks we have seen in the past are called custom layer abuses. Most of these frameworks like Keras, they provide the flexibility for you to add custom layers. Keras calls it lambda layers, and it allows you to insert Python code into custom layers. Attackers abuse these layers to call arbitrary system functions inside those custom layers. And these get triggered at the time of inference, not at the time of load. So you load the model and then you make an inference to make a prediction, at which time the malicious code get activated. And both pickle and the custom layers are largely mitigated at the moment because pickle format is discouraged from using, and most of the model scanners can easily detect pickle vulnerabilities and injections. And similarly, lambda layer is currently deprecated from Keras, and it is not serialized as well. And the third kind of attack we have seen in the past is called hiding invades. And the attackers cleverly use the model parameters to hide the malware. If you look at model parameters, they are nothing but floating point numbers. And their clever idea is to hide malware bits in the least significant bits of these floating point numbers, which does not affect the model performance or the accuracy. And when the user download this model, and they need to have an out-of-band triggering mechanism to assemble the malware and then launch the attack. And since it needs out-of-band mechanism and it needs white box access to the model, this attack is also not very popular at the moment. So with the knowledge of these existing attacks, now we are going to present the new attack that we designed, which has a blind spot on the existing model scanners. So our observation is these models, the TensorFlow models are still, even shared models, are executable computational graph, and we can identify legitimate hidden functions inside TensorFlow, and we can still chain them together in order to launch attacks. So what do I mean by hidden functions? Let me show it through an example here. So the first function, tf.io file read, is a common function, well documented. And if you use these kind of functions in your model, the model scanners easily detect them, any nefarious malicious activities, and flag it. But on the other hand, if you look at tf row ops fixed length record dataset v2, it's a hidden function, not documented, not meant to be used by regular users. And it has this latent functionality of reading files from the system. So, and someone can abuse it, and the scanners have a blind spot on these kind of hidden latent functions. And the key building blocks that you need to build any kind of malware is only 4. it's a file read to steal data, file write to drop payload and achieve persistence, and network send to exfiltrate the data from the local machine, and network receive to get commands and payloads from a C2 server. So our goal is to identify these building blocks from those hidden functions, not use directly available popular functions because they get flagged by the scanners. Finding this hidden serializable function is like finding needles in a haystack because TensorFlow library is huge and it's constantly being updated. And serializable functions are not well documented. These are the functions that get into the serialized model when you get the trained model and put it into a file. And detecting co-functionality with side effect are not documented either. That's what makes the attack evasive. So this is where we use an LLM-based agent to, along with a set of tools we develop, to identify hidden serializable functions. So this is the overall flow of our work. In the interest of time, I'm not going to go into the details. Please refer to our paper for the technical details of how we build this system and how we are using these tools which we built in order to identify hidden serializable co-functions from the TensorFlow API. So this shows a set of identified hidden serializable co-functions for the 4 categories I mentioned: file read, file write, network receive, and network send. So these are hidden functions. They are not, the intended purpose is not read, write, send, receive. They are supposed to be used for internal functions only, and they are not documented in the public documentations. So once we identified these hidden co-functions, it's kind of easy for you to construct attacks. Usually attacks are a combination of these hidden co-functions. So first, I'm going to show you a code snippet from our actual attack where we do stealthy data exfiltration. The full code is available in GitHub for you to check. So in this, I'm going to show you the key highlight of the code. And first thing for any exfiltration is to read the sensitive information from the system. For this, we use a hidden serializable read function. And then once you read the data into memory, we need to exfiltrate. For that, we use the hidden serializable send function. So together with these two functions allow us to get sensitive data and exfiltrate to an endpoint that attacker control. In this example, we show everything in clear. Attackers use even more evasive techniques like encoding these payloads and also using believably trustworthy endpoints, which will allow them to exfiltrate without getting blocked by URL reputation systems. And this figure shows that we uploaded the model to Hugging Face, and it was not able to detect as a malware, and it successfully verified that it's a good model to use. So the point here is they have a blind spot on these hidden co-functions. The second POC attack is on, again, this is also available in the GitHub. It's a malware dropper. So for malware dropper, we basically need 2 key functions. We should be able to read from the network and then save it to the local system. So we use a hidden serializable receive function to receive the payload from the attacker control C2 server. And then once we get the payload, we save it using the print v2 hidden serializable write function as shown here. All right, so we showed you how these 2 attacks are easy to construct once we identified these hidden serializable functions. So how can we defend against them? And as I mentioned, existing scanners have a blind spot to these kind of attacks, mainly because these scanners are looking for syntactic and signature-based detection. They lack semantic understanding of the code. So they don't understand the meaning of the functions used, especially those hidden functions with latent meanings. And also, they don't analyze the context and the flow of the computation graph. And Oftentimes, it's rarely the case only one core function is used for launch an attack. It's combination of multiple core functions, either read and send, receive and write, as I showed in the previous slides. So looking at the context can help detect these kind of attacks. And in the paper, we show how we can incorporate a code understanding LLM to scan these models and identify these kind of attacks and block. All right, finally, to summing up with some takeaways. So as I mentioned throughout the presentation, models are codes. Treat every downloaded model as untrusted executable code and embrace semantic scanning. We are not suggesting that signatures-based scanning is not useful. They are, in fact, the necessary first step for you to do the signature-based scanning, and then build tools to do the semantic understanding so that you can identify attacks abusing legitimate functions, which has side effects. And always follow defense in depth. You have to, we encourage you to scan every model and then run the models in sandbox in order to identify any evasive technique that we were not able to identify at the static scanning step. And finally, as part of being responsible, we in fact contacted Hugging Face and Google, the TensorFlow Hub. So Hugging Face got back to us and mentioned that they are further investigating the issue. And Google acknowledged that it is in fact possible to abuse, and they suggested that model scanners should step up to prevent these kind of attacks. So with that, I'm concluding our talk. And if you have any questions, please contact me through any of these contact details I have mentioned below. I would be happy to answer any question you have. Thank you very much for your time. Bye.